Hi, and welcome to the third set of notes for Unit 3, which I've called the microscopic view of the atom, and I believe Miss E and Miss Ham might refer to it as how we know or what's inside the atom. But you're going to be really looking for Notes 3 in your note packet. So you're going to want to spend the next few seconds here getting ready to get that note packet out. And if you haven't gotten your note packet out and you're not at Notes 3, where it says radioactivity yet, pause the video, go grab your packet, and get prepared to take notes. Okay, so we're going to start talking about radioactivity a little bit today. We're going to talk about the different types of radioactivity, and we're going to talk about specifically fusion and fission today. So in fusion, the definition of fusion is that when two atoms combine to fuse into a new atom. Basically, the protons and neutrons in each nucleus combine to form the nucleus of the brand new atom. And in fission, when you start with an unstable atom and you shoot it with a high-speed neutron, it's split into two new atoms. Fission means to break apart, and some electrons are also released. And we'll talk about those two types of radioactivity today. The other type of radioactivity is radioactivity decay, and we'll talk about that in a future lesson. But it's when an unstable atom loses energy by the form of radiation. And the three types of radioactive decay that you're going to be responsible for having some understanding of are alpha, beta, and gamma. Alpha tends to give off positively charged alpha particles, and those tend to be also known as helium atoms, and that little fish symbol there is what it is, basically an alpha symbol. Beta decay gives off negatively charged electrons. It's a large B with a tail off the end of it, and it's just it shoots off electrons. And then gamma radiation gives off photons. And we haven't discussed what a photon is yet, but for the time being, we're just going to say that they're high energy packets or packets of extreme energy. All right, so the first type of radioactivity that we need to spend some time talking about is fusion. And fusion occurs when two atoms combine to form a new atom. And in that case, the protons and neutrons in the nuclei of the original two atoms combine to make the nucleus of the new atom. So in the picture down below, we have two atoms working together, coming together. The first one is deuterium, and the second one is tritium or tritium. And those are both forms of hydrogen. One of them has just got a proton and a neutron, and the other one has a proton and two neutrons. And so what ends up happening is that when they are put into the right conditions, and they tend to collide, and the right conditions are intense and extreme heat. Oops. Those two atoms tend to form plasma. And plasma is a state of matter in which the positive nuclei is stripped of the negative electrons, but the negative electrons aren't lost. They're just in the area. So you have a bunch of electrons floating around and a bunch of nuclei, protons and neutrons floating around, and they create this extreme energy or very, very high energy state of matter, which is really important for fusion, because if the electrons are stripped off of the original atoms, in this case, the deuterium and the tritium, that allows the deuterium and the tritium to come close enough together to form a nuclei. And then when the heat is released or given off in the form of energy, the stable atom is then produced in the terms of fusion. In this case, it's helium. So here we have four protons, or I'm sorry, we have an atomic mass of 4, and it has 2 neutrons and 2 protons, and we have the element helium. There also happens to be, in this instance, a singular neutron that is just released as part of the energy. And as a result of that, we have this intense amount of energy released when we form 2 atoms together. Now, a couple of things that we need to make note of here. First of all, fusion tends to occur in stars. So in the universe, fusion occurs in stars. And so what happens is that at the beginning of the universe, we had a lot of hydrogen and a little bit of helium, and we started making more and more helium through the process of fusion. And then what ended up happening is that some of the hydrogen would combine with the new helium, and we'd start creating a little bit bigger atoms. And then over time, those atoms started to make bigger and bigger and bigger atoms through the process of fusion. But the only place that we know of in the universe that this occurs is actually in stars, which means it's currently impossible on Earth for us to have fusion occur, because the amount of heat required to fuse 2 atoms together like this is so great that it would be uncontainable, and we'd basically blow the planet up. So until one of you can figure out a way to do that, we are not going to be able to create fusion on the Earth. Now, there is an equation or series of equations that occur in order for us to keep track of fusion. So here's an example where we take a carbon atom and we take a fluorine atom and we fuse them together to make a much larger atom, which in this case is phosphorus. So when we're balancing these types of equations, we have to keep in mind that mass numbers and atomic numbers must be equal on both sides of the arrow. So in the case of carbon and fluorine, if I look at my mass number, basically it's going to be 13 for carbon and 18 for fluorine. And when you add that up, you get 31, which is my new mass number over on the product side. I'm going to take my atomic numbers, which are 6 and 9, and add them up, and I get 15, which is equal to my new atomic number. Now, the new atomic number, this number on the bottom, when I'm doing these equations, when I'm balancing these equations, is what dictates what the new symbol is going to be. So once I added up the mass numbers and once I added up the atomic numbers, I took my atomic number and I went to the periodic table. And on the periodic table, I found out that the element that has the atomic number of 15 is phosphorus. And that's where I got the P from. So it's not too difficult. It's just something that we need to practice. So this first one is exactly what we just did. So I'm going to kind of cross that one out, and I'm going to add a different one as a practice one. So I'm going to say that if I take a hydrogen atom and I mix it with a beryllium atom, the first thing I'm going to do is I'm going to take my mass numbers, which are the numbers on the top, and I'm going to add them together. 2 plus 9 is 11. And then I'm going to take my atomic numbers, which are the numbers on the bottom. 1 plus 4 is 5. I'm going to grab my handy-dandy periodic table, and I'm going to take a look and locate atomic number 5 on the periodic table. And when I do that, I see that I have boron. So in the very, very first example that I went through is the fusion of boron. Another example, the one below, which is sodium fusing with calcium. So what I'm going to do is I'm going to add my mass numbers together, which in this case is 23 plus 48. And when I plug that into my calculator, I get 71. So my new mass number is 71. I'm going to take 11, which is my atomic number, and 20, which is calcium's atomic number, and add them together, and I'm going to get 31. And so I'm going to be looking for an element with an atomic number of 31 on the periodic table. And I'm going to go all the way across, and I'm going to see that that particular element is gallium, Ga. And so on the right side, I have the same mass number amount as I do on the left side, and on the right side of the same atomic number amount as I do on the left side, which brings me up to my next one, which is I know what my product is, which in this case is beryllium, which has a mass number of 8 and an atomic number of 4. But on my left side, I don't know what hydrogen was fused with. So what I'm going to do is I'm going to take, in this case, 8 minus 4, and I find out that is 4. So my new mass number of my first element is got to have a mass number of 4, and I'm going to take 4 minus 2, which gives me an atomic number of 2, which tells me that in this particular problem, a helium atom was fused with another helium atom to give us a beryllium atom. So that's how fusion works. And again, it takes place in stars. It's almost impossible to happen on Earth, but it gives off tremendous amounts of energy. So the next thing that we need to talk about is fission. And fission is a little bit different. This one does occur on Earth, and it is something that we are able to have some type of control over. But it occurs when we take an unstable atom, the picture down below is uranium, is being shot with a high-speed neutron, just a neutron that we happen to have laying around in a particle accelerator. And we accelerate that neutron and we crash it into uranium, and for an instant it creates an unstable nucleus. And when it creates an unstable nucleus, that nucleus can't exist the way that it is, so it splits apart into 2 different atoms, which are more stable. But that splitting apart also creates a tremendous amount of energy, and it also gives off some neutrons. So what I'd like to do is I'm going to draw a line right here. So on my reactant side, or the left side, I have 1 plus 235, 1 neutron plus the mass number of uranium. So I have a total of 236 is my mass number on the left side. And on my left side, the atomic number is 92. So, and I'm going to also say, so this is like an intermediate step. This is where we have unstable. So, but on the product side, if I take 92 plus 141 plus 1 plus 1 plus 1, I get 236. And on the product side, if I take 36 plus 56 plus 0 plus 0 plus 0, I get 92. So when I'm balancing the fission reactions, I'm doing the same thing. I'm making sure that I have the same amount of mass number and the same amount of atomic number on both sides. The key here, though, is that there is a lot of energy released. And so this is an example of potentially starting a chain reaction. So any of these 3 neutrons right here could go and crash into another uranium atom and then start the process over. And so this is one of the ways that, for example, nuclear bombs or atomic bombs are created, is that they start with a seed, which is the original neutron, and that neutron creates an unstable nucleus with uranium or whatever radioactive substance that they're using, and then it produces 2 things that are a little bit more stable, but gives off 3 more neutrons that go on and complete the or continue the reaction with other uranium atoms, which is why they produce, the fission reactions tend to produce so much energy. So here is another example of a fission reaction, in which case I'm going to take a high-speed neutron and I'm going to crash it into uranium-235. And in this particular instance, I have 235 plus 1 is, again, 236 for my mass number. And for my atomic number, 92 plus 0 is 92. So if I take 144 plus 89 plus 1 plus 1 plus 1, I get 236 36 on the product side. And if I take 45 plus 47 plus 0 plus 0 plus 0, I get 92 as my atomic number on the product side. And so that's all we're doing when we're balancing fission reactions, is we're making sure that we have the same number of the same atomic number value on both sides and the same atomic mass or mass number on both sides. So here are a few examples. On the left side here, I have 235 plus 1, which is going to give me 236 for my mass number, and 92 plus 0 is going to give me 92 for my atomic number. I have 144 blank and 2 neutrons. So what I'm going to do is I'm going to take 236 minus 144 and minus 1 and minus 1, and I get something like 90. So I'm going to put a 90 here. And then I'm going to take 92 minus 54 minus 0 minus 0, and I'm going to get 38. So I'm going to put 38 as the atomic number of the missing atom. And then what I'm going to do is I'm going to go locate element number 38 on the periodic table, and I see that it's strontium. So there's my missing element. Down the next one down below is a little bit different, and then I'm trying to figure out the number of neutrons that are given off. But the process is still the same. I have 235 plus 1, which is 236, 92 plus 0, which is 92. So I'm going to take 236 minus what I know, which in this case is 154 for a mass number, and minus 72 for a mass number. And when I do that, I get a value of 10. 10. And if I take 92 minus 62 minus 30, I get 0, which is what we want. So in this case, the number of neutrons that are given off is a total of 10. So that one is a little bit difficult. Well, different, rather. And so now here we have californium, which is the last example. And in californium's last example, there appears to be no neutron present. And the issue with californium is it's so unstable by itself that it doesn't need something to create that unstable nucleus. So it tends to undergo fission on its own. So on the left side, I don't have to add anything, but I have 254 and 98. So I'm going to subtract what I know, which is 254 minus 108 minus 1 minus 1 minus 1 minus 1, and that gives me a new mass number of 142. I'm going to put that over here. And then I'm going to take 98 minus what I know, which is 44, and I get a value of 54 for my atomic number. And I'm going to go on the periodic table, and I'm going to locate an element that has an atomic number of 54. And in this case, that element is xenon. And so there you have it. Let's see, is there anything else we need to do here today? Nope, I think that covers it. So, all right, so you are going to have a fusion and fission worksheet practice where you're going to have to go ahead and identify the missing element on either the reactant side or the product side, and answer some questions about radioactivity. And if you have any questions, please make sure you contact your teacher. If not, good luck, and we'll go over this the next time we see you. And have a great day.